Yes, sir. I am.
Yeah.
Yes.
Yeah, I've started actually.
Okay. Thank. Okay. Yeah. Everyone, please mute Manji's mic. Okay. Okay. So today we'll learn ways to solve recurrence relations. Recurrence relations are very common in analyzing algorithms, performance of algorithms, and because many of our algorithm design techniques, you may have a glimpse already, or you will know as we go along in this course, that there are various algorithm design techniques like divide and conquer. So this approach itself is like divide your problem into smaller subproblems and recursively solve those subproblems, and then somehow combine the solutions of those subproblems to obtain a solution for the given problem. So the algorithm itself is like recursive, and when you try to analyze, say, when you try to know the time complexity of the algorithm, it is not a surprise that we will have a recursive relation, recursive equation, and that we need to solve. So just to motivate, for example, let's take the classical March sort algorithm. Let's take the classical March sort algorithm, and and it takes an integer array as input, a1 to n. Also, you can see the beauty of pseudocode. Now it's very simple. If the array contains only one element, it is already sorted. So that's the base case. I don't need to do anything. So if array contains more than one element, then I recursively sort the first n by 2 elements. So I'm taking the float of n by 2 and first n by 2 elements, and then the next n by 2 elements, ceiling of n by 2. We solve them recursively using the same merge sort. And then once I have these sorted subparts, I combine them using the merge routine. I will assume that most of you, all of you, know merge sort, which is true. I think if you don't know, don't worry about it. There are an endless number of YouTube videos on merge sort, lecture notes, and so on. Whichever medium suits you, you can learn merge sort, either from lecture notes or from books or from YouTube videos and so on. Now, we want to study the time complexity of the merge sort, worst case time complexity. So throughout this course, we will focus mostly on worst case time complexity, and we have discussed a few reasons in the last class why we want to focus mostly on worst case time complexity. Again, in the beginning, it is better to explicitly write what do we mean by time complexity. It is not the time in seconds. It is the number of steps, number of basic steps that the algorithm executes. And worst case means that it is a maximum number of steps. Okay, so let's count how many steps this pseudocode has. So the if statement is like one statement, one logical comparison. That's what I have written order one. So it takes constant number of steps. Then m equal to n by 2, that's also takes order one time. Order one means that anything which can be executed in constant number of times. Then from our definition, if Tn is the time worst case time complexity of merge sort for sorting n elements, then the first recursive call for merge sort takes T float of n by 2, and the second recursive call to merge sort takes T ceiling of n by 2. And then this merge subroutine can be executed in order n time. There are many algorithms, and all of them has its own beauty. So what is Tn? So Tn is the sum of all these steps. So Tn is T T of float of n by 2 plus T of ceiling of n by 2 plus order 1 for if statement comparison, then or plus order 1 for m equal to float of n by 2 plus order n for the last step merging. Okay, and now you know that is these three can be combined and written as order n. That follows from basic properties of big O notation. Big O of 1 is also big O of n, and big O of 1 is also big O of n. Big O of n plus big O of n is same as big O of 2n, which is same as big O of n. And if you apply again, that then you get these three sum is equal to big O of n. Now it's not sort of a very nice recurrence, because we have these floors and ceilings inside. So when we are given a recursive function and we are asked to find a closed form solution, what is the first approach that comes to our mind? Please feel free to unmute and speak. What is the fast approach, most naive approach? For example, this will be the syllabus for first class test, which is near the end of January, and for some reason, for some important work in Facebook or YouTube or WhatsApp, you are not able to study today's material. Then, but there is a question in the first class test. What will you do? Except cheating, because that's very risky. What will you do? What is your first approach? You have not learned, you have not read anything. What is your first approach to solve any recurrence relation?
Like test it for 1, 2, 3, and try finding out the pattern.
Correct. That's one approach. Like test it for 1, 2, 3, and so on. That's also can be a possible fast approach. Any other fast approach?
So you can also guess a solution and put it in the recurrence relation and check.
But that's very risky, because in
Yeah.
exam we have limited time. What guess? For guess also we need to, I can't guess, for example, I can't guess anything arbitrary, Means, for guess also we need some knowledge, something, but we have very important work in Facebook, WhatsApp, YouTube, and so on. We have, that I have not studied at all. So uh, for, for such a people like me, what should I do?
So like
Any other approach?
we took like topics like which take less time or less time consuming.
No. Forget time and everything. Now you think of it as a function. You are given so once you have written a recurrence relation by analyzing the pseudocode or algorithm, you can forget the algorithm. Now you want to solve this recurrence relation and get a closed form solution. Any the first approach, I'm very sure that many of you will try that approach. Yes, anyone?
So maybe I'll take n to be in this case maybe I'll take n to be a odd number and try to see a pattern like they mentioned.
Or I think this case is, because of this case it is confusing. Forget this case. I am giving you an arbitrary recurrence relation. As you know from Facebook posts that teachers will only do easy things in class, and in exam they will give hard things. So you can be best assured that in exam you won't get a simple recurrence relation like this. It will be much more difficult. So for arbitrary recurrence relation, very complicated. What will you do? You don't have any idea so that you can guess or do anything. What will you do?
So I think there's just one option then take the smallest numbers and try taking bigger and bigger numbers and then try to solve it.
Yes,
Like I solve for
that's
n equal to
that's one
2.
solution.
Yes, sir. That's
Yes,
so.
that's one solution. Okay, but the answer I was looking for is simply expand. For example, if I'm given, if I've written Tn equal to in terms of t of smaller n's, then I can apply the same definition on the right hand side again also. No, for example, I can apply expand this term and this term and so on. Keep expanding so that I can have t of smaller and smaller n's. Okay, so maybe the approach is, let me write. Most naive approach is unroll. Unroll or expand, simply expand. So let's see. But the problem with this expand is that for this particular case, this ceiling and flows. So for the time being, I can help you with one thing, that we can write. I can get rid of either ceiling or floor, because let's see. I'm only looking for upper bound. If I'm looking for upper bound, then I can replace this floor, T of floor of n by 2 with T of ceiling of n by 2. With a sort of working assumption that the number of steps will increase if the array size increase. So I replace T floor of n by 2 with T ceiling of n by 2. Okay. And then I have two plus. Now this order one, I also write it as Cn. Cn, this is for n greater than equal to n naught for some constant n naught. That's from the definition of big O notation. Something big O of n means that something which can be upper bounded by c times n for some constant c greater than 1, and this upper bound holds for all n greater than equal to n naught for some natural number n naught. That's just from the definition of big O. All of you with me? Catch me if I am doing anything wrong. Okay. Now again, it's sort of easier, but if I try to expand, then again this annoying ceiling will make my life difficult. So the good news is that we can ignore floors and ceilings safely. Ignore floors and ceilings. The the spirit why we can ignore floors and ceilings, because we are we are interested in asymptotic bound. We are anyway not interested in constant multipliers or additive constants. We are looking for what is the dominating term in Tn. But this needs to be formalized. This, let me write this way. This needs to be formalized, and especially in the first class test. If you ignore floors or ceilings without justifying it why or how we can ignore, then you will lose marks. I'll show you why and how you can ignore, but let me first write it, and then at the end of the class I will pathetically justify how and why I can ignore. So need justification, need formal justification. And this is end of the class. It will be done end of the class. Because for all practical purposes, and indeed after the first class test is over, you can forget this. You can simply remember this thing, that you can ignore floors and ceilings. That doesn't matter. So what is the recurrence now? Ignoring ceiling to T n by 2 plus cn. Now I can apply the naive approach of simply expanding. What should I do? This is 2 square t n by 2 square plus 2 cn cn. This is less than equal to 2 cube t n by 2 cube plus 2 square plus 2 plus 1 times cn. And this I can continue.
So
I can, yes.
would the 2cn term not be cn simply, because from the tn we're getting n by 2 outside, so each n by 2
Yes,
gets
yes, yes,
multiplied by the
correct,
2
correct.
outside, and
Correct,
that
I
would
think
follow
you are
for
right.
each and every expansion.
Yes,
So
yes, yes, yes,
yes.
correct, correct. Yes, you are right. Thank you. This will be Cn. Yes, yes, yes. Correct. Let me write this one. So this is 1 plus 1 plus 1 times Cn, and so on. So after log n steps, like log n base 2 steps, I will hit 2 to the uh, log n base 2 t1 plus 1 plus cn, and this is also log n base 2. So t1 is 1 because I don't need to do any recursive call. So here you can see that if n equal to 1, then it takes constant time or big O of 1. So so what is this? This is putting t1 equal to 1. This is n plus cn log n base 2, which is big O of n log n. Notice when you write big O notation, you do not need to write the base of log, because what the constant is already taken care of in the big O notation. Question: anyone who has not understood that this analysis, that the time complexity of March sort is big O of n log n? Yes.
Sir, why log n means number of steps? Why log n?
It's like n this. Let me use some other color. So this n is getting halved after each step. So for example, if n is 64, after how many steps you will hit 1?
Sir,
Like
6.
log 64 base 2. Yeah.
Yes, sir. Yes,
That's
sir.
why log n base 2.
Okay, okay. Got it, sir. Thank you, sir.
Any other question? And this is the crux of the matter. This is the main point of today's discussion. If you have understood this analysis, you have understood everything. Whatever I will teach today, you have understood it. You will understand it. It is not difficult at all. So what we will do in the rest of the class is little bit of filling up some formalities and generalizing it. Means here is that this 2tn by 2. What if it is 3tn by 2? What if it is say 4tn by 3? Something like that. What if it is 2tn by 2 plus, instead of cn we have cn square? Something like that. Okay. So let's generalize it. So the recurrence relation that we are interested in for algorithm analysis mostly or often has this sort of form, that Tn is less than equal to At n by b, the algorithm makes a many recursive calls on inputs of size n by b and make some computation, perform some computation, and that computation takes f of n time. So we are generalizing the recurrence relation of merge sort when a equal to, for merge sort recurrence relation, a is 2, b is 2, and f was cn. Everyone with me? So I'm just generalizing merge sort analysis of merge sort, and I will do the same analysis, exactly ditto same analysis, and we'll check what we will get. Let's try with the naive approach, because till now we know only naive approach, and that will be enough. Okay, so let's expand. Sorry, less than equal to a square t n by b square plus a f n by b plus fn. Okay, statement. Okay, very good. Again, expand. That's all what we know. A cube t n by b cube plus a square if n by b square plus a if n by b plus fn. And this will continue. Can someone tell me what will be the last step?
So a to the power log n to the base b t of 1.
Very good. Log n to the power base b, because this expanding will continue for log of n base b. After that, inside t it will be 1, and assume that t1 equal to 1. And then it will be a to the power log of n base b minus 1 f of n to the power n by log b to the power log of n base b minus 1. So last term is fn. And that's it. Now you see that it is not very convenient to work with, isn't it? It is no. It's very difficult to remember also, and that's why what we will do is that we will study some special cases where this summation has very nice form, and that will be called the famous master theorem. But this is the proof of master theorem, and this is and such a naive proof. Okay, so we'll study 3 cases when this particular summation is sort of very easy to analyze, but you will see that these 3 cases are not like exhaustive cases. It's not like whatever recurrence I will give and you expand, this is the sum what you will get. Now, if this sum falls to be among these 3 cases, which will happen in 99% of the time in algorithm analysis, uh, then you know the direct formula, and the formula will also come from here. So let's see what are the 3 cases when this sum is particularly easy to write. So case one, uh, if this series uh, decreases exponentially, if it so happens that this function f is such that this series is an exponentially decreasing series. What do we mean by exponentially decreasing series? Can someone tell me? What does this statement mean? When do we say a series is sorry, yes, please.
So the rate of change of the function is also an exponential function.
No, something in it's very easy. It's like a geometric series, but it is decreasing. So exponentially decreasing means that it's a geometric series and it is decreasing. That's it. That means every term is a constant factor smaller than the previous term. That's it. Every term is constant factors more smaller than the previous term. Then then what is the value of this series? What is this sum? Then what can we write? Tn is less than equal to what? Suppose
So
we have a geometric. Yes, please.
So
Yeah,
log n
Shan.
base b times fn.
Sorry, again.
So the log n base b times fn, it will be lesser than that.
You are saying log n base b times fn.
Yes, actually, I'm not sure about the times fn. Wait, I have to think.
Okay. Okay.
so
Anyone else? Yes.
so the a that we had is less than 1.
Uh, no, A, you see, here was A. A is not less than 1. So that's a good question. Yeah. A is greater than 1. It's like, and I'll assume A and B are integers. A is greater than 1, B is greater than 1. It's like, think of we are analyzing a pseudocode, an algorithm, which is like divide and conquer, and it is making a many recursive calls, and each recursive call is of size n by b. So both a and b is greater than 1. But that's not important.
So I think like log n base b times the first term, because the first term will be the largest because it's decreasing, and there will be log n base b.
Forget this. I think you are all giving more than due respect to this ugly looking series. Forget this. Just focus on what do you mean by a series which is decreases exponentially. Every term is constant factor smaller than previous term. Can you give me an example of such a series? Just concrete example. Give me an example of such a series.
Like 1
So
half 1 by
1
4.
half, yeah.
Yeah, so 1 half, 1/4, and so on. So what is the value of this sum?
So 2.
2. So it is like, okay, If it is finite, then less than equal to 2. Now, using this, which one is the, I don't know, I don't want to give more hints. It will be an insult to you.
So should B be greater than A?
No, you just use this fact that every term is constant factor smaller than previous term. That's it. A, B, all these are taken care of in that statement. You are going for what values of A and B, what relations between A and B, this series will be exponentially decreasing. But I'm not asking that. I'm asking you that suppose that the values of A and B are related in such a way that this series is exponentially decreasing. Then can you give me say upper bound of this sum? Okay, so if a series is exponentially decreasing, which one is the highest term? Which term is the highest term?
A to the power log n base b.
First term.
Yes.
It's just from the
Yes, sir.
definition. First term. Now, isn't a exponentially decreasing series the is a GPC a geometric progression? Is it the sum not dominated by the first term? Isn't it the sum is a constant factor of first sum?
Yes, sir.
Yes.
Yes, sir.
Isn't it easy?
Yes,
We
sir.
do not need to focus on relations of A and B. Use this term that the series is exponentially decreasing. So it is big O of the first term, A to the power log of n base b. Now we always like to write as n to the power something. So it is n to the power log of a base b. Anyone who has doubt, feel free to unmute and speak. Yes. So, you take any geometric progression. What does a geometric progression look like? A times R up to A times R to the power n. That's how a geometric progression look like. Now, this is a exponentially decreasing series if R is a fraction, if R is less than 1, in between 0 and 1. So what is the value of this sum? This value of this sum is A times 1 minus R to the power, I think n or n minus 1, something like that, by 1 minus R. Now, if R is a fraction, then it is like A. It is less than equal to like A by 1 minus R. If R is a constant fraction, it is big O of A. Are you with? So it's or you can just think that you can check that any geometric progression, any finite geometric progression or infinite also, any geometric progression, the sum is big O of the maximum term. Okay.
Yes, I got it.
The sum of any geometric progression is big O of the maximum term. Apply the same thing for the second easy case. When the series increases exponentially. Now, what do you mean by series increases exponentially? Now you all know. Just tell
Yes,
me.
sir. Every other term is a constant times greater than the previous
Correct.
term.
Correct.
And
Correct.
so
Every term. Yes. So Tn equal to?
So Tn should be equal to big O of Fn because
Very
now
good.
the
Very
last
good.
term will dominate the sum.
Last term will dominate. Is there anyone who have not understood and want me to explain? Please feel free to unmute and speak if you have not understood. Don't shy away. If you have not understood, then I don't know. This is easy, and it is my fault. I have not explained properly. This is elementary mathematics, and you are all good at mathematics. So superb, excellent in mathematics. You have all cracked IIT. So I'll again explain. If you have not understood this, please unmute and simply tell me. I will not. I'll simply explain it. There is
Hello, sir.
nothing fancy. Yes.
Yeah, it
Yes.
would be better if you explain it once again.
Yes. So we are analyzing the case when the series is exponentially increasing. Now, exponentially increasing means that it's a GP series, it's a geometric progression, and the multiplicative factor is greater than 1. That's it. Now, what is the sum of a geometric series? What is the value of a geometric series? It is dominated by the highest term. So, and you can prove that it's easy exercise that the sum of a geometric series is big O of highest term if R, the multiplicative factor, is constant, which is the case in this case. And we are assuming that a series is called exponential increasing is every term is constant factor higher than the previous term. So if every term is constant factor higher than the previous term, then which term is the highest term? Which term is the highest term if every term is constant factor higher than the previous term? The last term, right? Are you with me?
Yes, sir.
Yes. So the last term, and so the series will be dominated by last term, Fn. And same thing for the case one. If it is decreasing exponentially, then the highest term will be the first term, because every term is constant factor smaller than the previous term. So the series will be dominated by the first term, the highest term. So these are the two easy cases. Another easy case is all are equal. All terms are equal. Which was the case for March sort. Now, if all terms are equal, what will be the complexity? What will be Tn? What is Tn if all terms are equal?
And into the
Correct. It is take any term of your choice because all terms are equal. So the cleanest term is Fn, the last term. Let me take that. Fn times number of terms. What is the number of terms? It is the depth of this expansion, which is log n base b. It is Fn times log n base b. Base b I don't need to write because I'll put big notation. Anyone who has doubt in this part, please unmute and speak. These are the easy cases. Of course, it is very clear that on a bad day, on an unlucky day, you can get a recurrence relation for which the series is neither exponentially increasing or exponentially decreasing or all equal. Then you have to somehow try some other trick. But in most cases, for algorithm analysis, you will hit up among one of these three cases and you will very easily write this, easily solve these recurrence relations. Okay. So this is master theorem. So master theorem gives another sort of a condition in terms of A and B when the first thing will appear. another condition in terms of A and B when the second thing will be true. That means for what condition, what relation between A and B, the series will be exponentially decreasing. For what relation between A and B, the series will be exponentially increasing. And for what relation between A and B, the all terms will be equal. If you write those relations, then that's what you get is master theorem. That is bit ugly, but let me not write it. And I let you, I'll ask, request you not to see also. It is much easier this way, or you can, without seeing the book, you can try that on the what conditions, or you can check, you can see the master theorem, and you can map it that for condition one, the series is exponential. If series is exponentially increasing, then this will be second one will be the will be the solution. If some condition, if the series is exponentially decreasing, then the first one will be the solution, and so on. But this is the essence of master theorem. I will deliberately not write the conditions of master theorem in terms of A and B when these three corresponding to A and B, the relations between A and B, these three cases will occur. I will deliberately not write it because that will make it look difficult and look ugly and give you a false feeling that no, it's difficult. I have not understood. This is the core, that when this series is exponentially increasing, when it is exponentially decreasing, and when all terms are equal. Okay. Questions? Okay. So now let me, before going to another method, which is a little bit formal. In some sense, this method is not so formal. It's not completely rigorous in some sense, because you can ask many. Can someone raise some objections against this method? Can someone criticize this method? For example, for march sort, let's criticize this method. Suppose I'm the student and you are my teacher, and I have not behaved with you properly, have not attended classes. You want to cut marks. Now find some criticism, something, and find where you can cut marks for, say, for this simple analysis of march sort.
So like we have assumed that the n will be a power of 2.
Correct. Very good. You are assuming that n is power of 2. If n is not power of 2, then the in between terms are like fractions and those things, right? In the and also it does not make sense. You see, you have defined Tn to be the the time complexity of march sort, when worst case time complexity of march sort, when it is given an integer array of size n. Now for n equal to some non-integral value, say 20.5, this definition itself does not make sense. What calculation are you doing blindly? What do you mean by time, worst case time complexity of march sort, when it is given a array of size 20.5? It does not make sense. Very good. First criticism, and most important, very important criticism, and this is the criticism I was looking for also, that this is okay, this is fine only for n equal to 2 powered h, and h is some natural number. What about for other n's? Very good, I'm very happy. And that's why it is sort of like semi-formal. Often this fast level of expansion and this sort of thing we do, which is right, and often we do to get a feel what is the time complexity. And this is when you are mature enough, that's enough. And most of the time, almost always, you will find the right time complexity, and there is a justification to get away with this within the framework of this expansion, not going to some other method. That justification, beautiful justification, it is written in a footnote in algorithms book by Jeff Erickson. It is one of the reference books, and the PDF is legally freely available. Legally freely available. That's not a pirated copy or scanned copy, anything. From the author's webpage, you can go and download a free copy. That's an excellent book. You can read it. Let me not tell you the answer, with the hope that if you go to the book and read that thing, you may also hopefully read some other things also. So this criticism can be tackled within this framework, but I will use this as an excuse to introduce to you another method, which is like completely formal. It also takes care of floors, ceilings, also everything. And this is called substitution method. Substitution method, and these are the two methods only. But before that, let me tell one thing. Often, yes. Anyone? Yes. Questions?
So,
No, Ishan,
I
your
have a
voice is
question.
cutting.
Why is that
Yes.
very crucial? Even in the case where we're taking, so
No, your
so
voice is
I
cutting.
why is it that we consider to be a so I
No, Ishan, I can't hear.
connection. I'm
If
sorry.
if others have understood, can someone tell me his question? If others are able to hear,
No, his voice was breaking.
his voice was breaking. Correct. Yeah. Okay. Okay, Ishan, you try again after at the end of the class. Don't forget your question. So just before going to substitution method, let me just show what is called recursion tree. It is just the pictorial depiction of this unrolling or expansion. This is called recursion tree. So suppose you have a recurrence relation like Tn is A T n by B. Let me not do n by B. Let me do the beautiful one, Mart sort one. 2T n by 2 plus Cn is less than equal to. So the recursion tree is for every function call, you make a node in the tree. So this node is for the call when an array of size n has been fed. Now uh, in the Mart sort, two recursive calls are made, and recursive calls you denote it as subchain. These two recursive calls, and each node you denote it, you label it with the amount of time spent, amount of basic number of basic operations that has been carried out in the node except recursive calls. So if you forget this recursive call, if you forget this recursive term 2Tn by 2, the rest of the work is Cn. So you mark it as Cn. Now the two children corresponds to 2Tn by 2, these two terms. Now there, the work done at that level will be Cn by 2 each. And again, it will call T2T n by 4 and so on. This particular tree is called recursion tree. It's just a pictorial, nice pictorial description of total amount of work that is done. So in some sense, you can see that Tn is nothing but sum of the labels of all nodes in the recursion tree. And often with this pictorial depiction is so vivid, and it makes this computation so visible. It is very easy also to compute what is the time complexity. For example, often it is convenient to compute the time level by level. For example, in the first level, the time is time spent is Cn. The second level, there are two nodes, but the work done has also halved, so Cn by 2. So in total, for second level, the total work done is Cn, total time complexity. For the third level, I have 4 nodes, but it is Cn by 4. So if I add 4 Cn by 4, I again get Cn, and so on. And when will it end? What will be the depth of this tree? This depth of this tree will be log n, because the depth of this recursion is log n base 2. Okay, so this is called recursion tree. It is exactly same as like unrolling or unraveling, expanding the recursion, and it's just a pictorial view. Questions on recursion tree? Okay.
So
Yes.
we are ignoring the Tn by 2 term, or is it getting
No, we are
included
not. We are
as
not
we go down?
ignoring it. We are just writing in the child node. So in the recursion
Okay,
tree,
sir.
yes. So this is like Tn by 2. Use some other color. So this is Tn by 2. This entire box. This is another Tn by 2, and this Cn. Okay. Okay.
Sir,
Yes.
sir, if we try to find the value of Tn using the recursion tree, we will be getting Cn log n, right?
Correct. Correct.
But when we calculated above this, we got n plus Cn log n.
Yes. Big O is same. Both are big O of n log n.
Okay, sir. Okay, I got.
Yes. And it is even for this case you won't get it. Is just maybe you see if we do it if we read it carefully, maybe the number of terms maybe here it is log n minus 1, something like that. Don't believe my calculation. Never believe my calculation, especially these plus 1 plus and something like that. Don't believe them. Okay, so now let me go to the next method, which is like completely formal. Teachers cannot cut marks. If you feel that you are having a bad time in life, every teacher is cutting marks, and in exam you are given to solve a recurrence solution, use this method, and then teacher will not be able to cut any marks. Substitution method. Substitution method. Substitution method. It is like, so let's again, as teachers always do, they show the method on the simplest example and you have to do the harder examples. So again, let take the March sort example. Tn is less than equal to 2Tn by 2 plus Cn. C is some constant greater than 1. Okay. Now, the substitution method is that you need to be a little bit expert. It's like you already know what the solution will be, but only because of that bad teacher who want to cut your marks, you want to write a formal proof. So like in this records, I know that it is big O of n log n, but I need to prove it formally. So what I do is that I'll prove by induction. So you will often see that whenever we are doing that expansion trick, series expansion trick, if you want to make it more and more formal, the most formal way is to apply induction. Then that's the most formal way. For example, if I want to ask you, what is the sum of 1 plus 2 up to n? Of course, you can you will explain to your friends that that you see the pattern. For different values of n, you see the pattern or two, and then something n times n plus 1 by 2. But if someone really pushes you formal, give me more formal. Okay, you want more formal? Then okay, by induction. Let me prove that sum of 1 to up to n is n times n plus 1 by 2. I'll prove it by induction. That is completely formal. No gap. That is what substitution method will do. Okay. And what to do? Okay. Let me do this. So we guess that let guess the first step, which is the most difficult or non-trivial step for substitution method, is to guess the solution. It's like I want to know the solution, but you are telling me a method which starts with knowing the solution. This is, I guess that this is less than equal to, I know it is big O of n log n. So it must be like less than equal to some constant times n log n. So let me write C1 times n log n. I'll find out what value of C1 I should put. Any constant will work. So let's see. For the inductive step, the base case will be taken care of by assume T1 equal to 1. And the base case is taken care of. So for inductive step, Tn. So I have assumed that this case works till n1 to n minus 1. Now I will prove it for n. So Tn equal to less than equal to 2T n by 2 plus Cn. So by induction hypothesis, I know that Tn by 2 is less than equal to C1 n log n, 2 C1 n by 2 log n by 2 plus Cn. This is equal to C1 n log n minus C1 n log 2 plus Cn. Please catch me if I am doing some mistake. Now I'll be happy if this junk is not there. If this I want to write this is less than equal to C1 in login. Now this junk will go if I put so choose. That's why I have not put C1 beforehand. Now I can choose C1 conveniently. C1, let me choose C1 equal to C by log. Because C is a constant, C1 is also a constant. And if I choose C1 to be this, then my induction works. And if induction works, I have proved that for every natural number n, Tn is less than equal to C1 in log n. And that's it. That's what I am supposed to prove. Question on substitution method. You see how neat and clean this method is. The only difficulty is guessing, and it is very important. Sometimes, you know, we apply this recursion tree and this method, and we get a solution. But if we are not convinced, for example, here and there we are doing something. For example, here I have replaced floor with ceiling. So the assumption is that time complexity increases if the array size increases, something like that. And so if we are not sometimes if I am really unlucky, if this series is not one of these three, then it is very difficult to compactly write it. Then I can always write it, but is that is that right or is that tight, something like that, or can it be improved? So all those testing can be best done using substitution method. So whenever you have a upper bound or any bound, and you are not sure, sure yourself, then you can simply test it using substitution method. Questions on substitution method?
Sir, is there any general method to guess this Tn less than C1 and log n? This one.
Which method?
How we can guess this one?
Yes. The
C1
only
and
method, yes. The only method I know is recursion, that unraveling and unrolling expansion, whatever I just taught before substitution method. That's the only method I know.
okay, sir.
So in my opinion, okay, for example, if I am given to solve a recurrent solution and I have no clue about the solution, what I will do is that I'll first apply that simple naive unrolling method and try to get that. Now, if I am convinced that I have done rightly, then fine. But still, if I want to be sure, then I can verify my answer with substitution method.
So,
Okay, sir.
I did not understand the part about choosing C1 to be C by log 2. So how is it that we're choosing C1 to be something?
It is this way. It is like you have done this. Now, again, teacher is so merciless to me that he can use this excuse. So in exam sheet, you cut this. No, I'm not choosing anything. You cut this also. And write, I will prove that Tn is less than equal to C by log 2 this. And everyone you instead of C1, you write this term. It is like my guess, C by log 2.
So, but how have we proven our guess?
Just a minute. Yeah. C by log 2. C by log 2. Now you see that these last two terms cancel and this math works. Now tell me your question.
So, but how does this prove our guess? It's like a oh, okay.
My guess is Tn is less than equal to C by log 2 times n log n. That's my guess. You can't ask me from where I got this guess. I have some superpower. I guess this.
Okay, sir. Okay,
And
sir.
this is the proof.
Okay, sir.
This is the proof. Okay. Any other question?
Yes.
Otherwise, the only thing that I owe to you is that how can I remove formally these ceilings and floors? Ignore ceilings and floors. This I need to prove, and that's it for today. And again, let me again repeat, till fast plus test, if you ignore without the steps I am doing it, formal proof, then we will deduct marks. It will just get you habituated that, just in your lifetime, you will only know this, you will only practice this only for this 15 days. After 15 days, the fast plus will be there. So for 15 days, you see that this can be done formally. Okay, now let me remove this floor, this ceiling formally. Not as a friend, but as a teacher. Okay. So I have what? I have a Tn is less than equal to 2T n by 2 plus Cn. Now what do I do is that I again, okay, I'll always assume that T is an increasing function. That means if I replace the argument of the function with something higher, then the value of the function will only increase. So I will let me replace ceiling of n by 2 with n by 2 plus 1, an upper bound of ceiling of n by 2. And this inequality is fine. Now, okay, I have got rid of ceiling, but now I have an annoying plus constant, and it is no good. It is no good. So now what I can do is what is called change of domain, domain transform. This trick is called domain transform. This color I like. Domain transformation trick. What is this trick? Nothing magical. It's like you define some other function s of n as t of n plus alpha, where alpha is some constant. Alpha I'll choose again later. So as the requirement dictated me, how should I choose C1? Let the requirement dictate me how should I choose alpha. So let me keep the freedom of choosing alpha later, depending on the requirement. Okay. Now you see that this is this. Now you apply this recurrence for Tn. By applying this recurrence for Tn, I get what? Tn is less than equal to 2t n by 2 plus 1 plus cn. So this is less than equal to 2t n by 2 plus alpha by 2 plus 1 plus c times n plus alpha. Everyone with me? Now help me write it. Write this in this term t of n by 2 plus alpha by 2 plus 1 as a function of s, not t. Now can someone tell me what should I write? S of what? If Sn equal to Tn plus alpha, then
Alpha
T
minus alpha
n.
by 2, n by 2 minus alpha
Very
by 2.
good. You know, from S to T, I need to add alpha. So saying the same thing in different way, from T to S, I need to subtract alpha. So when I go from T to S, from the argument, I need to subtract alpha, and I get minus alpha by 2 plus 1 plus C n plus alpha. Now I got a recurrence in terms of S. Let me write it clearly here. Sn is less than equal to 2s n by 2 minus alpha by 2 plus 1 plus c times, c is not a function. Don't misunderstand. C times n plus alpha. C is a constant. Now I got a recurrence in terms of s, but here also there is the same annoying constant term plus on top of it there is some alpha. My life looks much difficult. Can someone tell me what should I do?
We'll choose alpha 2, then there will be
Very good.
nothing.
Choose alpha. Choose alpha so that this is 0. So choose alpha equal to what? 2, I think. And this will be 0. Alpha is a constant. I am choosing alpha equal to 2. So I get this is 2 s n by 2 plus c n plus 2. Okay. And solve this recurrence. Now it is a beautiful recurrence. So for this we know how we can solve. We have many methods like unrolling and recursion tree and substitution methods. We know all the how we can solve these things. This is in our domain now. We solve this and we know that this looks like Sn is equal to Sn equal to big O of n log n. We all know this. But we need to solve for Tn, no? So how should I do? Tn is equal to, from T to S, I need to subtract alpha. So Tn equal to S n minus alpha, and alpha is 2. And what is big O of n minus, Sn minus 2 is big O of n minus 2 log n minus 2. If you expand, big O of n log n minus 2 minus 2 log n minus 2. Second term you can ignore. The dominating term is the first term, and log n minus 2 is dominated by log n. This is big O of n. Question. Now you know formally why we can ignore safely those floors and ceilings, when we are only interested in asymptotic behavior of the function that we are finding closed form. Questions? Okay, so if there is no more question, so that's all for today. Within 1 or 2 days, I'll post the first assignment and exercise problems, practice problems on the course webpage. It is on this uh, elementary proving elementary properties of big O, big omega, theta, and those sort of asymptotic notations. Just playing with this, getting used to this, and solving some easy recurrence relations, easy and interesting recurrence relations. I'll send an email, broadcast mail after I post. Okay, so if there is
upload the
yes.
slides also.
The slides I have uploaded now. Last class's slides are available on the course page now. PPC slide also I'll upload within 1 hour, I think. My not slides, my write-up. This write-up, last class's write-up is available on course page. Write-ups will be there on course. Sorry, for this week I was outside campus, so that's why it got a bit delayed. But now I've returned and it should be on time. Any other question? Okay, so if there is no more question, so let's stop here. Somebody can stop the recording. We'll meet again on Monday at 12 o'clock. Okay. Thank you for